Bem-vindos ao Type Theory for All podcast. This is your host, Pedro Abreu, and in this episode I have the great honor to interview Professor Benjamin in Delaware. And in this episode we talk about what is PL, why does it matter, why is it cool, what is the Lambda calculus, what is type theory, who was Church, who was Alan Turing, what's the Church-Turing Thesis, what's the Curry-Howard Correspondence, what's propositions as types? What are proof of system? Why are they cool? Why do we even bother talking about that? That and much more coming up next. This is my great pleasure to introduce Professor Ben Delaware. Professor Ben is an assistant professor at Purdue University. He got his master's at University of St. Louis under Aaron Stump, working with sound and complete decision procedures in COC. Got his PhD at University of Texas at Austin, advised by William Cook and Don Battery, working on feature modularity and mechanized reasoning. He got his postdoc at MIT working with Adam Shipala, and he worked on deductive synthesis of abstract data types in proof assistant. Nowadays, you can find him as an assistant professor at Purdue University, and I have the great pleasure to be advised by him. You can also follow him on Twitter at GhostOfBendy. Thank you so much for coming today, Ben.
Well, my pleasure, Pedro. Glad to be here.
I have a question that I don't think I ever asked you this, but what is Ghost of Bendy? What is that?
Well, back when I got started on Twitter, Bendy was already taken. So I needed some variant of Bendy. So I went with Ghost of Bendy. There's a more involved story. I could tell you. So this was right around Twitter was getting hot. And someone started a joke account at UT called Ghost of Dijkstra. And so they posted a bunch of sort of grumpy tweets in Dijkstra's voice. So people who aren't familiar, Dijkstra is a famous computer scientist. He was a Turing Award winner. And he was sort of famously curmudgeonly, I guess is the word for it. He was sort of, let's go with curmudgeonly, right? And so I think he passed away in the early 2000s, 2000, 2001. Anyway, but in many ways, his spirit still haunted the halls of UTCS building. And so one of my fellow grad students started up this joke account to sort of post curmudgeonly tweets about computer science. It was called Ghost of Dijkstra. And so I riffed on that to create Ghost of Bendy.
That's hilarious. I really like it. I'm glad that I asked that. So let's get started with talking a little bit about your experience on how you got in programming languages research. How was your experience? How did you end up doing all of this?
Yeah, so this is maybe going to be a long story. So I was always very interested in learning different languages growing up. So I was interested in learning a lot of different programming languages. So I started off with like QBasic, and then I learned Pascal. I was really into Perl for a while, C, C++. I did a lot of assembly programming on calculators. So I was just like dabbling in all of these different programming languages.
Oh, I'm sorry about the assembly programming.
I was actually, no, it was good. I think maybe we'll get into this later when we talk about programming, sort of what is programming language research. But one of the advantages of doing sort of the assembly level programming was that it really forces you to get to the down to the computer level, the machine level, and really understand basically what's going on under the hood. And when you're doing assembly programming on a TI 85, 84 calculator, you sort of you have control over everything. I mean, you have to manually manipulate the buffer representing the display, right?
You really have to learn that in a deeper level, right? Like really have to understand what's going on. Yeah.
Yeah. I mean, there was no compiler, so you were literally interfacing with the machine at like its most basic level, right?
Mm-hmm.
Right. And so the other thing I was actually interested in studying human languages too, right? So human languages, natural languages.
Natural languages.
The phrase. Yeah. So I learned Latin in middle school of all things, and I took Spanish. I dabbled a little bit in German, and then I studied Russian of all things in college, believe it or not. So I don't know, what is the phrase for this? Linguophile? Something like that. So I was really into studying new languages.
Polyglot.
Let's go with that. So yeah, and I actually was very interested in doing computational linguistics when I was doing my undergrad, although we didn't have a computational linguistics program at the school I was at. So I took a lot of like sort of linguistics classes to augment my computer science classes. And I guess what I was really interested in there was always, the idea of learning a lot of different languages appealed to me sort of because they all get at this sort of fundamental truth of how we communicate, right? How do we communicate with other people? How do we communicate with machines in the case of programming languages? And there's this observation there that there are many different ways of communicating, and all of them are valid, and all of them have strengths and minuses, and there's philosophy behind all of these things. And so I was very interested in sort of the meta study. I sort of gathered all these points, right? And now I wanted to do I was very interested in sort of the meta study of these languages. What is the theory or the science of communication, right? And so that's why I was interested in linguistics. Right, so that was sort of the PL side. So how did I get into PL research? So the other thing I was really interested in undergrad was AI, because everyone's interested in AI, right? That's always been the cool thing.
Always,
Yeah,
yes.
it's different flavors. But when I was interested in AI, I was particularly interested in symbolic reasoning. So this was more old school AI, like Wumpus World style things, SAT solving. These were sort of the, A-star search, that sort, yeah, game playing, basically.
Hmm.
These are the sort of aspects of AI that really interest me. So when I did my master's, I took two classes. So but my first semester, I took actually, I took three classes. I think this is interesting. So the first one was a statistical machine learning class. I was really stoked about, right? I was really excited to be learning like cutting edge machine learning research. And then I also took an HCI class of all things, right? And then I also took a class with Aaron Stump, who, as you mentioned before, was my master's supervisor, on automated deduction. And if I remember correctly, the class was something like automated reasoning, intro to automated reasoning. I was like, I like reasoning, right? And I really didn't enjoy the statistical machine learning class that much. It was all like, I don't know. I've never been a big fan of statistics. It's all just sort of number crunching. I'm like, meh. But I really found this automated reasoning class. It was super appealing. Like we looked at decision procedures, we looked at study of logic, mathematical logic, and then we moved on at the end of the class into looking at dependent type theory. And we actually played around with Coq back when, which is an interactive proof assistant for sort of doing reasoning inside of using a computer as a tool. And this was way back in 2005, I guess it was. So Coq was
So you didn't do any abstract algebra, number theory, anything like that before this course? Is that
abstract. No, I did take a number theory class.
proofs?
Oh, proofs. Yeah, but they're all pen and paper proofs, right? So
Well, sure, but it still gives you that flavor, right? Like
mm,
it's this flavor of doing
yeah,
proof, right?
yeah, I guess that's a fair point. Um, so I certainly, as part of my CS degree, I took all your favorite sort of discrete math class. I took a number theory class. I did take an abstract algebra class, all the calculi, linear algebra on top of abstract algebra. So I was familiar with doing proofs from that, right? But I guess the difference is, hmm, maybe I don't even know if it's a difference. One of those things about like mathematical proofs is, I'm gonna get into trouble. I want to say they're somehow like divorced. It's very navel gazing-y, which is funny thing for me to say. But your the proofs you do, the sort of formalized reason you do is all focused around the math, like this sort of the subject domain, right? And math, pure math is very sort of, it's self-consistent. And you're not actually talking about reasoning about the real world, the outside world, all of these things, right?
Makes sense.
And so, hmm, this is why I think maybe I found, the AI thing more appealing. I was always into games too, right? So this idea of reasoning as playing a game was very appealing to me. Yeah, and so I guess indeed when I took this this automated reasoning class, I guess we were doing mathematical proofs, but there the sort of the game playing nature of the proofs became more apparent to me, right? It's like, how do we codify a reasoning process? How do we develop strategies? What are the rules that you can use to sort of explore this space, right? And that sort of really drove me. And further on top of that, how do we sort of embed all of this reasoning, all of this knowledge inside of a computer, right? And enable the computer. How do we teach a computer to reason, basically? Teach might be a little strong.
Exactly. No, yeah, it's basically teaching a bunch of rocks how to do math, right? Like how to reason, how to actually become actually kind of smart and infer new things,
Right.
right? So yeah.
I mean, this is right. I mean, this is if the essence of being a human is our ability to look at the outside world and draw inferences and make plans, like that is reasoning, right? That is essentially what automated reasoning is, equipping computers with the tools to do that.
So this leads me to my next question. So, okay, now that we understand a little bit more what is this reasoning about, teaching the computer to reason and to infer new things, to gather new knowledge and to
Hmm.
learn or rather prove things soundly, like gather new sound statements, right?
Hmm.
Given a set of things that you already know. That gives me the first question. What is programming languages research? What does it have to do with all of that? Where does that come in?
Yeah. So I guess this sort of ties back into my um, does this tie back into like that original statement? I said these three classes were all sort of related, and I mentioned HCI, right? I took this human computer interaction class that was very much focused on like user interface design. But the reason this is connected to the automated reasoning and programming languages is that, from my perspective, a programming language, like its sort of fundamental, like core concept, is it is a programming language is the interface between a human, maybe probably the programmer, right, and a machine, right? So this is the mechanism by which we, as people, sentient beings, communicate with machines. This is how we make them do stuff. This is how we program them, right? And so the role of, I think, programming languages is fundamental to computer science, because without a language that you can use to tell a machine what to do, it's useless, right? If there's no algorithm, it's just a bunch of bits, right? Or qubits, if you're using a quantum computer. And so programming language research really has three legs, right? So the first one, the most maybe not the most fundamental one, but so the one that commonly comes to mind is, how do we design this interface, right? What is the right way to design a language potentially, or some other interface for interacting with a machine, right? What are the right, if we're designing a programming language as sort of a standard programming language, what are the right features? What are the right abstractions that we can build into this language that make it easier for a human to communicate with the machine, right? So the first leg of programming language research is really the study of how to design these languages. I would say it's sort of an HDI question, although I don't think a lot of
Mm-hmm.
pure PL researchers would necessarily agree with that, right?
Then I can see how a lot of compiler work come into that, parsers, you know, all these languages that are being built all comes into that first leg.
It actually, so I argue that the second leg is the sort of the compilers, right? Because so you've got this interface, right? Now, how do you actually take whatever you've written down and turn that into something the machine understands, right? How do you interpret that and produce something that the machine can actually execute, right? Because by itself, a program is actually just a string of characters, right? And so you need to parse it, you need to extract some structure from it, and then you need to convert that into effectively a series of bits that are loaded into a register, as the machine executes. I mean, that's very simplistic. I mean, there are so many different aspects that go into, you know, compilation like these days, right?
Right.
Very
Oh
rarely
yeah.
are we like it's not just a matter of, compiling a program to run on one machine anymore. It's a matter of, you've got a system, you've got configuration files. You want to deploy this program
You've
in
got
a
to run it.
distributed setting. Yeah,
You've got to
yeah.
run it in your browser. You've got to run it in your mobile phone. Yeah.
Yep.
You've got to
And like,
optimize your code too, sometimes obfuscate. So there's a lot of stuff going on nowadays. Yeah.
yep, right. Security concerns. And each of these different sort of aspects of the program, like even when you get to this level, right? You don't have a single programming language anymore, right?
Mm-hmm.
You're like, if you think about like a database backed web application, right? It's typically, well, you've certainly got the control logic, right? So you've got some program written in whatever your favorite language is. I don't know, Java or something. We'll just say Java. I don't know if that's anyone's favorite. But then you have like SQL, so you have a language for interacting with the database system. You have probably a bunch of configuration files, sitting around the back end that actually specify how this database is set up, right? Where the servers live. I mean, and then assuming it's like a web, you also have HTML for doing the layout, doing the view. You have CSS. You have all of these things. So programming languages. There are many different programming languages that actually need to be used in order to implement a single program.
So the second leg, the first leg, you would
Yep.
say that is this realm of actually coming up with the language and just like the high level details and how things should play along. And the second level is actually bringing that down and implementing and making making sure things will work and things will go around. Something like that.
Yeah, that's right. So that's exactly right. I would say it's like the design of the language itself. The language itself is an object of study.
Mm-hmm.
Then there's the implementation of the logic of not the logic of the language, right? The question
We'll
of
see
how
later
you
that's
write
it's
a
a logic, but yeah.
right, right. And then so the third thing I argue and is reasoning about programming languages, right? So there's always this question of I've got this program, does it do what I want, right? I feel like this is sort of an intrinsically necessary part of programming language research because how can you be sure, or how do you have any sort of assurance that this program actually is semantically meaningful, right? It actually does something you care about, and moreover, only does the things you care about, right? It doesn't sort of exhibit any sort of auxiliary behaviors. And so this like second leg or this third leg is there are so many things that fall into this. Testing at some level falls into this. How do we develop good tests that actually flex the desired behaviors? But on top of that, how do we design type systems that make sure we aren't, generating, type errors at runtime, right? How do we?
This actually brings me to the question: why do we even need types at all?
Right.
Why don't we just run a machine code and like is types even important?
I mean, if you don't care about programs doing what you want them to, then I mean, sure, who needs a type, right? If you don't,
Why?
let me draw that back a little bit here. I would say types are a fundamentally useful tool and natural abstraction for ensuring that your programs do what you want them to, right? And you could get by without types, certainly. You could get by without tests, right? I wouldn't necessarily recommend it.
Yes.
Right? But here's my view on types. So at a really high level, I think types define the meaningful programs of your programming language, right? So by itself, without a type system, you can write down any sort of gobbledygook you want in your language, in theory, right? If your language is sufficiently rich enough, it's not just like a calculator language, like a, arithmetic expression language, right? It should be possible to write down programs that don't mean anything, right? And so what the type systems do is they allow us to sort of classify in an intuitive way the meaningful programs, the semantically meaningful programs of our programming language. And here we define semantically meaningful programs to be the ones that don't sort of exhibit these undesirable behaviors.
And one undesired behavior that is very common for we to not want is, for example, the program crashing randomly on good inputs, right? So let's say I know that my function will work on integers and will always return me an integer. I don't want this program to just crash during runtime, during execution, right? I want some sort of guarantee that things will run as I want to. So this is what you're saying about what's the word you said? Semantically meaningful or
Semantically
right?
meaningful, yeah. Yeah, I think that's good. Like even on top of that, just outside of crashing, imagine a language where you can just cast everything to something else, right? And you write like a plus function, and you could pass it a string of bits, right, and add them together. But garbage in, garbage out, right? Maybe that's not quite the right example, right? So just imagine you just like, oh, I'll treat everything as a string of bytes or bits, right? And it'll do something, but the user doesn't know what sort of the expected inputs of that function are, right? They're not really sure if they're getting garbage, they're putting garbage in,
Right,
right?
right.
So even if it doesn't crash, they might be getting garbage out. So they don't have any assurance about that, right?
Right. So it's like a gatekeeper saying you can only use this function if you assign to this contract, if you guarantee that what you're giving me makes sense to what I expect. So some sort of that's what we call the interface, right? And some sort of
Yeah,
contract on
yeah.
that.
I yeah, I don't like gatekeeper because gatekeeper. I mean, gatekeeper. I mean, there's you could take sort of an antagonistic view of types, right? Where the type checker is always sort of
That's exactly that's my point. That's the type checker, the compiler will be this gatekeeper that's like, no, this is not acceptable. You're not gonna run things with this input. Like if you give me a string, I'm not even gonna compile your program because this is bogus. It makes no sense. Go away.
yeah. I prefer to think of it more as like a friendly fellow who's like, uh, you should probably give me integers, right? This is what I expect, right?
I don't think compilers are very
Um,
friendly. I don't see that. They're usually very mean and
well, I mean, error messages are a different problem, right?
yeah.
I think, yeah, I could go off on a tangent about that, but
Okay, so you mentioned that with types now we can actually gather more guarantees about our program. So we've been talking about how we can get some assurances, right? Like if I understand correctly, as things start getting we get richer and more precise types, then it seems to me that we can reason more
mhm.
about what our program is supposed to do. We can reason more about how things come along and how does that come together? How does that where does that come in and how do we build that? What do we mean by richer type systems? Like what's actually going on here under the hood?
Mhm. 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 Yeah, that's a good question. What do I mean by a richer type system? Hmm. Okay, there are two ways we can go with this. So when I say richer type system, what I really mean is that it is a type system that allows you to judge that a larger set of programs are semantically meaningful, basically. So, and continue to provide these sort of assurances about their intended semantics, I guess. So maybe you might also sort of enhance the sort of set of what it means to be semantically valid. So here's a non-lambda calculus example that probably seems old hat at this point, but back in the day, before Java 6 or 7, Java didn't have generics, right? So if you had like a list, right, of elements, you always had to every list just had a set of objects in it, unless you wanted to go and specialize it, right? And so whenever you wanted to interact with one of these collections, you had to do a cast, right? In order to make sure that whatever you pulled out, if you had a list of integers, you would have to cast it to integer to make sure there were no type errors, right? And this could generate a runtime type error because casting can fail at runtime, right? So these casts were sort of like an escape hatch. Maybe let's not get into that, but you could easily write this well-formed program that always would never have any of these sort of runtime errors because you only ever put integers in the list and so that means you would only ever pull integers off the list, right? But there was no way to sort of explain this or justify it using the type system, and so you had to insert these casts to sort of use an escape hatch to convince the compiler that this thing is type correct. And then we added generics, right? And so now you had this new sort of abstraction, and you enriched the type system in such a way that you could type this entirely new class of programs, right? Well, I guess it was the same class of programs, but now you could justify that they were correct and ensure that they didn't have these runtime type errors, right? So now you were able to provide similar guarantees about a wider set of programs. And so that's what I really mean by a richer type system. Here, I mean that you're able to do two things. I guess you can type a larger sort of class of programs, show that they're well formed, that they won't have these typing errors. But now you can also provide sort of stronger guarantees about the runtime behaviors of these systems as well, right? And so richness goes in two directions, right? So let's think about let's just real quick go to the lambda calculus. So The Lambda calculus, just as a sort of quick intro, was this fundamental model of computation that was developed by Alonzo Church in the 30s, right? And it's sort of analogous to Turing machines, right? So these two concepts of computation are actually equivalent, right? So anything you can do with the Turing machine, you can do with Lambda calculus and vice versa, right? And the Lambda calculus, has basically a language where everything is a function, right? All you can do is call functions, all right? So it's possible to, in the regular Lambda calculus, the untyped Lambda calculus, to write programs that loop forever, which can be problematic, right? So one way to avoid this is you can develop a type system for the Lambda calculus that allows you to ensure that every Lambda term, if it types, is terminating, and in fact terminates to a unique final result, right? That is, the Lambda calculus is strongly normalizing. So you have this simple type. So you have the simple type system, but there are certain programs that always terminate and terminate in a unique normal form that are not typable by the system. So now we can start adding more things, sort of enriching the type system. And there, like, the first natural step is actually to add something very similar to what we added to Java. When we added generics, we added these type parameters, right? And so to the Lambda calculus, you can take the simple type system. It's literally formally called the simply typed Lambda calculus. And now you can add abstraction over type variables, which means we can essentially abstract functions over the type of arguments they take or the result type, right?
And that's called System F, right?
System F, exactly right.
Good.
Right. Or the polymorphic Lambda calculus, two different.
Right. Yeah, they were kind of created both in France and here in the US at the same time, so they got two different names, right?
Yeah. Well. Yeah. So I mean, there's an example. So you can actually start off with this really simple. Well, it's actually this very powerful model of computation. You have this very simple type system that can only show that certain small programs are well typed. And then we can start adding new features or new typing construct, new concepts of the type system, and we can start typing a larger and larger class of programs, which all enjoy the same properties as the simply typed Lambda calculus: termination and strong normalization. Yeah, so that's what I mean by richer type systems.
So you're saying that in a sense, the Lambda calculus is better to develop your language than a Turing machine. It seems to me that in some sense it's easier to add new things and to make it kind of stronger and like have a stronger type system. Why do we even use the Lambda calculus? What's so interesting about it?
Well, this is like a philosophical argument. It's going to get it. I mean, so why do we prefer Lambda calculus over Turing machines?
It seems to me that the reason is because it's very simple. It's very simple to add, like, and to reason about it, right? Like the logic behind it and the inference rules is very close to what we do in logic, right? So all this too in logic we can already use for kind of free, right? And then it kind of brings us to the Curry-Howard correspondence.
Yeah, I mean, I agree with you philosophically, but it's definitely a subjective argument, and I think. Here's my take on it. I think Turing machines, like that model of computation, is much closer to the machine, right? It feels very, very much like you're programming. Well, I mean, you're programming an abstract computer, right?
That's how you model your computer. That's how you model things in the real world, and that's how things should be made to execute. Yes, I agree with you.
Yep. And so there are more details associated with the Turing machine. It's a little. Let's just leave it at that. And sometimes those details are quite nice if you're talking about like complexity theory, right? It's very natural to talk about,
steps,
complexity classes, steps, computational things. Space it's very easy to talk about space and using Turing machines, right? Because you have the tape or tapes. Yeah. But when you want to abstract away those details, when those, like, who cares about the sort of underlying memory of your machine or whatever, right? I think that's where the Lambda calculus shines, right? It definitely gets rid of a lot of those details without sacrificing computational power. And so that way, the Lambda calculus is sort of like the Haskell to the Turing machine's assembly, but maybe that's not appealing. So I don't know, the Java, no. You're sort of your higher level programming language. It's a little bit closer to how humans think as opposed to how machines think.
I see.
If that makes
Yes,
sense.
that makes a lot of sense. That makes a lot of sense.
But that's purely a subjective argument. I mean, there's also this idea that type theorists or people who do programming language research, or certainly a large class of them, sort of are descendants of Alonzo Church, uh, including like
That is a
academic
very
descendants, right? And so they
yes.
inherited his model of computation, whereas the people who do complexity theory are all, well, actually, I don't know if they're descendants of Turing or not, but probably they're from that school of thought, right? So I
Hang
mean,
on. No, no, hang
in
on. Yes.
fact, you are a descendant of Alonzo Church. I'm pretty sure.
I don't consider myself a descendant of Alonso Church because you did your master's with a descendant, you did your postdoc with a descendant, but you didn't do your PhD with a descendant. So I would argue that I'm not a descendant.
Okay. Well, you're from the school, right? I mean,
Yes,
that's definitely
yes.
the school
But
you're
hang
from.
on, hang on. If we're
Yes.
talking about
Okay.
this philosophy between Turing machines and Lambda calculus, I would disagree with you because Alonso Church himself said that Turing machines are a better abstraction for modeling computers. So I don't know. And also another argument for Lambda calculus to work on this space is that we don't see the same work being done in compute in Turing machines. So even though maybe yes, it is a philosophical question of just well, people are just inclined to keep doing what they were doing. At the same time, we don't see the same things happening in Turing machines. And it seems to me that if it was in fact the same thing, it should be happening at some point, and people should be kind of doing that just like to prove a point or because it's kind of fun or something. But mm,
This is getting into a sort of
yeah,
philosophy of
too
science thing,
philosophical.
right?
It's
So, I mean,
yeah.
that's the set of questions that like PL researchers are interested in are and want to do research in are sort of and they're not disjoint, but they're different than the sort of questions that a complexity theorist want to do, right? And so the sort of research questions they're working on, they're less interested in sort of the questions we're working on. And so when they want to work on those questions, they tackle it with the tools they have at hand, right? Well, this is funny because there was a line of research called typed assembly language, probably about 2 decades ago at this point, right? Where you're adding types to assembly language basically, and doing proof carrying code and all that stuff. But people don't really add types to assembly, right?
Well,
And so there are
yeah,
a lot of types for
yeah.
Turing machines.
There you go. Okay, so
Yep. Anyway, yep.
going back, we started touching this point of this difference and similarities between Turing machines and Lambda calculus. So if I remember correctly, the story behind what was happening here was okay. We had Alonzo Church at Princeton in the 30s and a little before that, working on logic and all of that, and he came up with this nice, how can I say, model of computation called the lambda calculus, and he could say, yeah, this is what we actually mean by what programs or algorithms is about, and there's this whole story going on. And at the same time, and literally the same year, this guy Alan Turing came up with exactly the same solution but in a very different modeling, and it was now known as the Turing machine, right? And
Hmm.
then, if I still remember correctly, Turing got in communication with Alonzo Church, and he actually came to the US to do his PhD under Alonzo Church. And then they proved that these two models are actually modeling the same mathematical structure, if you can say that way, right? They're actually doing the same thing. So the lambda calculus is actually doing the same thing as the Turing machines. So all this correspondence between the lambda calculus and the Turing machines got known as a Church-Turing thesis, right?
Hmm.
That's
Hmm.
beautiful. That's really, really cool. So everything that you can do in a Turing machine, you can also do in lambda calculus. Okay, so since we are working with lambda calculus and that's what's happening, this leads me to the next question, which is, so is this what we're talking when we say type theory? It's literally working on lambda calculus. What's type theory?
So what is type theory? So I'm going to be maybe a little bit more abstract, and then we can get more specific. But really, when we talk about type theory is any sort of, I'm going to say, formal system. So it's a system with a set of rules that identify a series of operations that can be performed on particular terms. And by a term, I mean some object, right? So it's a way of equipping objects with a type that dictates how you can interact with it, right? And type theory is the study of these formal systems for assigning types to objects, right? And so commonly when we think about type theory, usually people are referring to, assigning types to lambda calculus terms. I mean, that was where it really got its start, right? So we identified a set of operations that can be performed on these lambda calculus terms and what they support. So the type theory for the simply typed lambda calculus is uber simple, right? If everything is a function, right, you can really do two things with it. You can either call a function, right? So you can call it with some arguments. So you can use it, or you can build a function, right? And these are sort of the dual ideas behind type theory, I would say in general, is this idea that every category or type, really, every sort of thing that you've classification or set, can either be used, right? It can be eliminated as a popular way of saying it, or it can be built, right? And a type theory defines how you can build things of a certain class and how you can use things of a certain class. And the whole goal of type theory, I would say, is making sure that you build things and use them in a way that's consistent with their classification. Yeah, so let's say, so with functions, you can imagine you have a type of functions, right? So what can you do with a function? You can define a function or you can call it, right? Numbers, what can you do with numbers? Well, that depends. But if you have an integer, generally speaking, you can, let's say you can add it together, right? So, or you can test if it's zero, maybe, and then you can
So
say,
what you're saying, you're basically building kind of a game of what we can do in this system, right? And so we're
yep,
kind of playing this game inside our type system, saying these are the operations that we can do, this is the things that we can actually perform, and here are the rules, right? And then
these
we
are the
call
rules. Yep.
this. So this, you're basically talking about the inference rules. If anyone is a little familiar, we saw
Yep.
those bars, and you have all the assumptions, and you get to the conclusion giving this formalism, these inference rules, and then
Yep.
and then and then we start getting to the realm where we can actually now reason, actually use these rules to reason of what's going on. Is that
Mm-hmm.
right?
That's exactly right. That's exactly right. Because if a type system is just a series of rules, I mean, that's a reasoning system, right? How do we reason? Well, if you do deductive reasoning, right, that means you have a set of ground truth and a set of rules for deriving facts from that ground truth, right? And that defines the set of all true things according to your system, right? And that's what a type theory lets you do, right? It defines a set of rules and make sure you apply them in a consistent way, in a correct way, according to sort of the definition of those rules, and allows you to check that you've applied them in a consistent way.
So
Right.
what we're getting at here is that now our type system is such a cool thing that we actually have a logic behind. So now it's both something that we can compute and also you can reason. So is that what they call the Curry-Howard correspondence? The what's the name? The proofs are programs.
Programs
What's
as
that big?
proofs, programs as proofs, types as propositions, and it's occasionally called no, never mind. Yeah, we'll go with Curry and Howard isomorphism. Yeah.
Proofs as
Um,
programs. Who said that? Who was the who created that logo? It was a big name, right?
uh, I'm gonna get ahead of my
Anyways.
skis if I claim it was. Well, I mean the concept was probably floating in the ether for a while. I mean, it really
Yeah,
was, right?
definitely.
Like
Definitely.
folk and
Someone just like made this
some,
nice
yep,
shiny logo. Proofs are as programs.
yep, yep,
Proposition as
as
types.
types. Yeah.
Cool stuff. So it seems to me that we're actually building this formalism, this language where we can both program in it. We can come up with, addition, with string concatenation, with lists, and all the things that we do in our favorite programming languages. But now it seems to me that we're getting to such a rich realm, such a rich type system. It allows us to also reason about what our programs are doing now. And it seems to me that this is where the proof assistance comes in. Is that right? Is that
Here, so what is a type theory? So a type theory is a set of rules that you can codify, right? And more importantly, you can sort of use them to judge whether or not a program makes sense, like going way back to our original thing, right? And more importantly, usually when you develop a type theory, you have this limited set of rules that you can then mechanize the process of making sure that something makes sense, right? So we call this type checking, right? And so this observation here is that as our set of types grows richer, right, as we can classify more and more things to define broader classes of programs, right, we can also mechanize the process of checking whether a proof makes sense. We can mechanize the process of doing reasoning, right? Because if going back to the analogy, if we can interpret a type as a particular proposition or claim, right, then the question of checking whether or not a proposition is true boils down to seeing if there's some sort of program, there is a program that has that type, that inhabits that type. By codifying the system, the like reasoning system, sort of a formal way, that allows us to embed this inside a computer. It's mechanizable, it can be reasoned about within the computer, and that's at the sort of heart of interactive theorem proving or theorem proving in general, right? It's like we're going to equip the computer with a set of rules that it can use to carry out reasoning, and it will be able to sort of check whether or not a sequence of reasoning is well formed by making sure that the rules were behaved, right?
Right.
Or were followed.
So that's basically where our favorite proof of system come in and allow us to do that and actually get our hands dirty and actually deal with those inference rules ourselves and play this game, right? Like then it starts becoming this process of actually playing the game and actually building these proofs, right? Building this inference by using the inference rules, by using the rules that this game allows us to use. Then we can prove things. We can build these propositions.
Mm-hmm.
And building this proposition is nothing but, so since we saw that proposition are types, right? So building proposition is not but coming up with a program that satisfies that type, right? So building a proof is basically the same process of building a program in a sense, right? Like it is building this term, this program that witnesses that type, right?
Yep.
That actually brings us to another discussion that is kind of, I don't know if it's still hot, but it's been hot for a long time in our field, which is this idea of intuitionistic logic and classical logic. What
Mm-hmm.
was that discussion all about?
I would say the idea behind, say, intuitionistic logic, or I like to think of it as constructive logic, is
Right.
this idea that every proof, every program, every proof slash program, right? Because these ideas
There's the
are
same.
interchangeable, can be evaluated or computed, right? So let's think about it this way. So let's imagine we have a function that takes some a's and gives us b's, right? So that's it. So its type is a arrow b in standard simply typed lambda calculus, but yeah. And so what this is saying, you could imagine, you can actually interpret this as a witness to this of a proof, right? This function says, if you give me something of type A or some proof of A or some evidence of A, I will build you up some evidence of B, right? And you can imagine that if this is truly a function, you can take an object of A and execute the function and actually build up sort of the evidence of B, right? And so this is the idea behind constructive logic. It's that every proof can actually be interpreted as a computable function that can be run. Every proof that you care about can actually be executed to build up the evidence for the particular thing you care about. All right. Now, in classical logic, there's this idea that every proposition is either true or not true, right? This is also called the law of excluded middle. So it is sort of an axiom or a fact that's assumed to always be true that allows you to say something like either the sky is blue or it's not blue. Either it's raining or it's not. Either I am a human or not, right? Or maybe more interestingly, either this Turing machine halts or it doesn't, right? All of these claims are admitted under this rule, this axiom of classical logic. Now, the problem with this axiom is that it doesn't have any computational content associated with it, right? it doesn't allow us to, it doesn't give us a procedure that will always either build the evidence that something is true, that the sky is blue or it is not blue, right? For an arbitrary proposition. And why is that? Well, it's precisely for that last example that this is a problem. Because if we had that, we could run this axiom, we could compute, for a given Turing machine, whether it halts or it doesn't halt, right? We'd be able to execute that program and then get out a proof of one or the other. Then we could examine what that proof is and say, this halts or it doesn't, which is obviously a contradiction, right? This would be literally a solution to the halting problem. And so the issue with classical logic is that it admits certain axioms. There are certain facts that you can derive that don't actually have a computational interpretation associated with them. And so what this basically means is, under the hood, if you can imagine, you've got this axiom is sort of like an oracle, right? It's like this external function that you can call, and it's going to tell you either this is true or not true, right? And when we're running this proof, if this proof somehow uses this axiom, it's going to make this call to this external oracle, but it doesn't exist. We are unable to link this program, if you will, with the function that actually decides, that fact. And so the program, in some sense, gets stuck, right? It makes a foreign function call, and we don't have an implementation. So this is not an executable program anymore because it relies on this interface, this unimplemented interface. In fact, this unimplementable interface, right? In general. Now, there are certain classes of things that are decidable, right? Where we do have decision procedures for. So if you sort of restrict yourself to the decidable facts, right?
Wait, what's decidability again? What do you
mean? So by decidable here, it means there is a function that says either this fact is true or not true, right?
Right.
So what's an example of something that's decidable?
This number is 1 or 0.
Yeah, there we go, right? Equality on numbers without multiplication.
Mm-hmm.
So this is decidable. So if you sort of restrict yourself to decidable theories or decidable claims, now your logic is, you can admit this axiom because it's no longer an axiom. And why is it not an axiom? It's precisely because we have this function that will either tell us yes or no, right?
You can always build
so we
this
can actually
function.
link.
Yes.
Yeah, you can link it against that implementation, and that'll allow you to run this program to its.
But so in general, we cannot do that for everything that we have. There are classes of things that are not necessarily decidable. Is there an easy example of that?
Classes of things that are not decidable.
Yeah, class of some simple example that is undecidable in general.
It's piano arithmetic, right? Or is it Pressburger? I always mess this
you
up.
mean the what about the piano arithmetic?
Well, so when I say piano arithmetic, it's a language of claims about integers. Let's say natural numbers with successor plus multiplication and, let's say, equality and probably less than or equal to.
So what's not decidable about that?
Well, there are certain facts in that logic which you cannot decide whether true or false.
There are some propositions that are undecidable there.
Exactly right. Mm-hmm. And certainly every sort of, in almost any theory, you should be able to decide. There should be very large classes of things that you can tell whether are true or false, right?
But in general, you cannot assume that all of your propositions inside of your theory are decidable.
Exactly right. This is like Gödel's incompleteness theorem.
Oh,
right.
Nice. I want to make an episode just about that later. We're getting closer to the end of the episode. I think we got. Okay. I am very, very happy with this conversation. I think this went even better than my expectations. I am so glad for you to come. Is there anything else that we should touch? Is there anything else you think it was not polished enough? Is there anything else do you feel was out, should be mentioned?
No, not really. I was going to make some pitch about how, like, you asked why proof assistants are cool.
Yeah. We can go back to that.
So one of the reasons proof assistants are cool are precisely because they allow us to they let us give us a way to let machines reason about stuff, right? This is a tool for helping, machines make deductions, reason about the world surrounding them, right? And what's cool here is that once you sort of equip, a machine with the ability to do this, now it can accelerate science in interesting ways, right? So if you think about like stuff like vaccine discovery, right? So there's like a lot of people that have been working on maybe vaccine, but so things like vaccine discovery, now scientists are able to, posit different chemicals or compounds and then ask a computer, what will happen if I, add this one or that one? And now they have these, rather complex models that allow the computer to sort of help answer that question, and they can test this all inside the computer without having to do any sort of experimental validation, right? So the tool, the computer is a tool that helps people reason about the real world, right? And I view interactive like theorem provers or proof systems as like a logical algorithm, right? These are sort of the tools that will equip us with the way of enabling machines to help us answer like entire huge broad classes of questions, right? We're not there yet, right? But once you get there, you can imagine, your computer helping mathematicians discover new and interesting, facts about under math, right? Answering questions about physics, about string theory or something, right? Which is pure math, but whatever. So I'm not sure that came out as polished as I want. I wanted to get people like say theorem proving is just like another form of building up, like enabling computers to help us help people, right? This is like a bad analogy, but like imagine playing chess or something, right? So we taught computers how to play chess, right? We equipped them with these things, and now they can beat any human, right? Well, most of the time, right?
Yeah, fair
And
assumption.
we taught at some level we enabled machines to learn how to play Go, right? And we, now they're better than humans,
Yeah, finally.
right? So finally, right? So we've at some point, once you equip computers with the right tools to reason, well, they can be better. This like theorem provers could be responsible for the singularity, right? Carried to its natural conclusion.
So hang on, you're just the opposite. You just got it unexcited about theorem, but this is dangerous now.
So that's dangerous, but let's go back to the vaccine thing. I think this is really interesting where you can actually they can help people answer questions. They can explore things that you couldn't on your own, right? So I don't think these baked into these tools, these interactive theorem provers, there isn't a lot of opportunity for discovery, right? There is a lot of opportunity for you to find a problem in a search space, right? And the computer helps you sort of explore that search space, right? And I think that's where it's interesting. This really is an aid for reasoning, exploring things that you just couldn't on your own,
That's
right?
beautiful.
And so here, this is like, it really is a proof assistant, but it is an assistant. This enables
Yeah.
you to interact with the computer in a very fruitful way to,
Now I can see that your claim back before, that is this your nice friend that will help you to go through your proofs, right?
right.
The proof assistant is this nice friend that will put you in the right path. Is always making sure that you're running on the right path and you're not gonna do stuff that does not make sense.
Yep.
Yeah, theorem improvers are usually nicer. They have most of the time they have nicer messages.
Again, error message is like a completely different, that's like its own
Fair
podcast.
enough. And there's also but anyways, so also there is this another very cool thing about proofs, about type theory and proof assistant, that sometimes is a little hard to get out to the outer public. And I actually got this from the Aaron Stubb podcast, that he was mentioning that. So when we're talking about mathematical propositions that are proven, it's not up for discussion. There is no point of views here. Maybe there are some philosophical discrepancies, but if you agree what the theorem is saying, that's it. It's done. It's over. And a big example that comes to my mind is like the Cantor paradise, right? Like when Cantor proved that their infinity is bigger than the others. This was a big thing back in the day. A lot of mathematicians were like, "This makes no sense. This is bogus. This is garbage." But they could not argue back. They were like, "Well, but I cannot find anything wrong on his proofs. Everything is sound here. It makes sense. So we have to accept this, even though we don't agree, even though we don't think it makes sense. It is what it is." And
Mm.
that's the big power of logic, the big power of what we're doing with type theory, the big power of what we're doing in proof assistant, in my point of view, is that proof assistant is providing us with this perspective, with this tooling that will allow us to keep us in the right track to finally get to these bigger propositions that will not go wrong. It's not up for discussion.
Mm.
And as you mentioned, in a sense, it's different than what we do in, say, biology and natural sciences, where there's a lot of experimentation, there's a lot of point of view, there's a lot of theoretical reasoning going on. Here things are it's just in this game. You set the game, you set the rules. If you agree that things are modeling what you think it is modeling, and you come up to conclusions, well, first you usually prove that your model is sound, that your model doesn't have holes, and then if you get to a conclusion, you're done. You're done. There's no discussion.
Yep.
Over. Right.
I think the last point you made is a very good one. Once everyone's agreed to the rules of the game, then you have to accept the result of the game, right? So if you prove something and these rules are reasonable and people say they're reasonable, then you can't argue with it. Now you can argue with the rules, but that's
exactly, yes. You can argue that it's not modeling what you expected that it was modeling, but you cannot argue with the game or the player.
Yep. Yeah, I was gonna say it's a good observation that you can't argue with the player, right? Like,
yeah,
who definitely cares what they did? They followed the rules, so
they follow the rules.
Hopefully, yeah.
Yep. I think we really could wrap this up on a high pitch, on a high note. This was an amazing conversation. Thank you so much for joining me. Thank you so much for enabling me to give this very nice introduction to what is PL research, of what is type theory. We talked about lambda calculus. We touched on the history of computer science. God, we talked about everything that I had in mind and a little more, honestly. Thank you so much for your time, Ben.
Yep, my pleasure.
This concludes our second episode of the Type Theory for All podcast. If you don't agree with anything we said, or you think we made any imprecisions and you would like us to correct them in the next episode, which I will do, leave us a comment at www.typetheoryforall.com. And if you like this episode, make sure to share it with your friends. You can find us on Spotify and iTunes and Google Podcast. But if you want me to list it anywhere else, please reach out. I will make sure to provide to your needs. I am staying here because my thesis will not get done by itself. I hope to see you next time.